Welcome to this explainer. Today, we're diving into the invisible architecture that actually keeps our favorite digital platforms online. Think about it. Whenever you stream a movie, grab a deal during a massive flash sale, or honestly, just load a popular web page, there's this brilliant, hidden system working tirelessly behind the scenes to make sure everything feels instant and seamless to you.
To really grasp why this matters, picture a typical e-commerce site. Maybe on a normal day, they handle around 5,000 users. But then they launch a massive promotional sale. Almost instantly, they get hit with a crazy traffic spike, rocketing all the way up to 1 million concurrent users.
If that website is relying on just one single web server, yeah, it's a complete disaster. Without a solid strategy in place, that server's CPU is going to hit 100% immediately. The memory completely exhausts, database connections max out, and users are left staring at endlessly spinning loading wheels. Eventually, the whole system just crashes to a halt. The business bleeds money, and frustrated customers bounce to a competitor. Okay, so here's our roadmap for how we'll break this down. First, the traffic bottleneck problem. Second, we'll look at core architecture and algorithms. Third, layer 4 versus layer 7 routing. Fourth, we'll explore modern cloud setups and Kubernetes. And finally, we'll look at real-world scale with Netflix. All right, part 1, the traffic bottleneck problem, and defining the hero of our story. So what exactly is a load balancer? Well, think of it kind of like a super popular restaurant. Hundreds of hungry customers are showing up. If everyone tries to order through just one cashier, that line becomes an absolute nightmare, right? But if you have multiple cashiers and a dedicated restaurant manager standing at the front, directing arriving customers to whichever cashier has the shortest line, suddenly everything flows perfectly. A load balancer is essentially that manager, but for computer networks. It manages incoming user requests instead of customers and routes them to servers instead of cashiers.
Or to put it in another way, it's basically like a traffic police officer at an incredibly busy intersection, actively directing vehicles down different roads just to keep everything moving. By intelligently routing those requests, it guarantees that no single path and no single server ever becomes a bottleneck. That improves your application's performance, pumps up your overall availability, and allows the whole system to scale efficiently.
Moving right along to part 2, core architecture and algorithms. Let's see how this actually works under the hood. Every single time a client request hits a website, it first hits the load balancer, triggering this incredibly precise, millisecond-fast workflow. Step 1, the client sends the request. Step 2, the balancer instantly evaluates which backend servers are healthy and actually ready to take on traffic. Step 3, it applies a specific mathematical routing algorithm to pick the absolute best target. And finally, Step 4, the chosen backend server processes the request and shoots the response back through the load balancer. This entire loop happens continuously, making sure requests are safely caught and routed without the user ever noticing a thing.
Now you might be wondering, how does it actually know which servers are safe to use? Well, before it routes any traffic, the balancer acts like a very strict doctor. It continuously runs what we call health checks. So for example, it might ping the servers with a test HTTP request every 5 seconds. If the server replies with a standard HTTP 200 OK, great, it stays in the rotation. But if it doesn't respond or throws an error, the balancer instantly yanks that sick server out of the traffic pool until it recovers. No sick leave allowed on the floor, which ensures no user is ever routed to a dead end.
Okay, so we have a pool of healthy servers. How does it pick one? It relies on algorithms. You could just distribute traffic equally using round robin, which literally just goes sequentially. Server 1, then server 2, then server 3, and repeats. Simple, right? Or you could use a smarter algorithm like least connections. This one actively monitors the servers and dynamically selects the one that has the fewest active connections at that exact microsecond. That is incredibly useful for applications with long-running user sessions where some servers might naturally get tied up longer than others. But hey, in the real world, your servers probably aren't all identical. So you can use weighted round robin. This lets you configure the load balancer to send more requests to your most powerful machines. If server A is an absolute beast with 16 CPU cores, and server C is a smaller machine with only 4, the load balancer will intelligently route a proportionally larger chunk of the traffic to server A. That way, you're never wasting back-end computing power, and you're never accidentally crushing your weaker machines. All right, section 3, layer 4 versus layer 7, and how we start adding real intelligence into the mix. Network traffic routing basically happens at a couple of different layers of the OSI model. Layer 4 operates at the transport layer. It relies on very basic information.
things like TCP or UDP protocols, source and destination IPs, and port numbers. It is blindingly fast and super efficient because it doesn't waste a single microsecond inspecting the actual application data. Layer 7, on the other hand, operates up at the application layer. This provides deep, highly deliberate, intelligent routing because it actually takes the time to read the request itself, looking at the specific URLs, HTTP headers, and even cookies. And that intelligence, that is exactly what makes Layer 7 so powerful. Because it can read the actual URL path, it makes highly targeted decisions. For example, it can grab any traffic heading to the /images URL and send it over to a dedicated cluster of image servers, while taking traffic headed for /API and routing it to a completely different group of specialized API servers. It's essentially organizing your traffic based on the actual content the user is asking for.
Layer 7 also bails us out of a pretty critical user experience problem: session persistence, also known as sticky sessions. Think about it. If you log into a website and hit server 1, but your very next click gets routed over to server 2, you might suddenly find yourself logged out. We absolutely need users to stick to the same backend server to maintain their session state. We usually manage this using 3 common tracking methods: dropping a tracking cookie, hashing the user's client IP address, or assigning a specific session ID.
There's another massive perk to this setup, and it's called SSL Termination. Encrypting and decrypting secure HTTPS traffic actually eats up a ton of computing power. By offloading that heavy lifting, doing all the decrypting of secure traffic right at the load balancer level, it can then just forward normal, unencrypted HTTP traffic internally to the backend servers. This saves an immense amount of CPU power, freeing up your backend servers to dedicate 100% of their resources to simply running the application.
Which brings us to Section 4, Modern Cloud and Kubernetes, where we move away from hardware and fully into software.
Back in the day, load balancers were these massive, expensive hardware appliances that you literally had to bolt into a server rack in a physical data center. Today, not so much. Most organizations have ditched the physical hardware in favor of highly flexible, managed software services provided by cloud vendors. We're talking services like AWS Elastic Load Balancer, Azure Application Gateway, or Google Cloud Load Balancing. These services automatically scale up on demand, handle health checks effortlessly, and they integrate flawlessly with modern DevOps workflows.
And when we jump into a modern containerized environment like Kubernetes, the routing logic gets even cooler. Traffic generally flows from the user to an external load balancer, through an ingress controller, into a Kubernetes service, and finally lands on the actual application pods. This exact multi-layered flow is pure magic because it allows an application to scale up by instantly spinning up new backend pods during a traffic spike without ever changing a single thing about how the end user accesses the site. Now, you're probably thinking, wait a second. If literally all the traffic flows through this one load balancer, isn't that a massive single point of failure? Absolutely, it is. And to ensure that balancer doesn't crash and take down your entire company, engineers design for high availability. They'll run multiple load balancers simultaneously in either active-active or active-passive configurations. That way, if one balancer suffers a catastrophic failure, boom, another one is already online and instantly takes over the traffic routing.
Let's wrap things up with Section 5, Real-World Scale, looking specifically at Netflix.
Just imagine the exact second a highly anticipated new series drops on Netflix. Millions of users press play at the literal exact same moment. First, global DNS acts as an initial traffic cop, routing the user to the geographic region closest to them. Then, a massive regional load balancer catches that request. It instantly runs its health checks, applies its algorithms, and routes the user to a healthy application server. When millions of people do this at once, autoscaling automatically spins up brand new application servers, and the load balancer seamlessly folds them right into the rotation. This deeply layered architecture is exactly what ensures smooth streaming for everyone without a single hiccup.
So, there you have it. We've seen how load balancers truly are the unsung heroes of scalability, reliability, and performance. From simple round-robin logic to highly intelligent Layer 7 routing and massive cloud-scale deployments, it really leaves you wondering. Considering the sheer, mind-boggling scale of global web traffic today, with billions of requests flowing every single second, what other brilliant and visible systems are working tirelessly in the background right now to keep our digital world seamlessly connected?